In this video, I have a special guest for you. His name is Stem Cell, and I gave him a shout out in the last video. But now he's back with Fourier Transforms, so don't forget to subscribe to him, and now, enjoy.
An audio signal is made up of sounds of many different frequencies, and a Fourier transform is a mathematical way of finding out what those frequencies are. But this technique can be applied to any function, not just audio signals. For example, I want to find the Fourier transform of a Gaussian function. The Gaussian function is sometimes called the bell curve because of its distinctive shape. This shape can be described with a simple mathematical formula. F of x is equal to e to the power of minus x squared over 2. And I want to write the Gaussian function as a sum of a number of different sine and cosine waves. Because I want to look at a continuous range of frequencies instead of a discrete range of frequencies, instead of using sums, I'm going to use integrals. So that means we want to write our Gaussian function as an integral over the entire range of frequencies, so from minus infinity to infinity, of the cosine function multiplied by an amplitude a that depends on the frequency, plus an integral over the entire range of frequencies of a sine wave multiplied by an amplitude b that again depends on the frequency. So a and b are functions that determine how much of a certain frequency contributes to producing a signal that looks like a Gaussian function. We can combine both these integrals into one integral by remembering Euler's formula that relates sine and cosine waves to the exponential function. And that gives us f of x is equal to an integral over the entire range of frequencies of c of omega, the amplitude, multiplied by e to the power of I omega x. And it's this function, c of omega, that we call the Fourier transform of f of x. And because there's a symmetry between a function and its Fourier transform, we can invert this formula to get an expression for c of omega in terms of an integral involving f of x. That is, c of omega equals 1 over 2 pi multiplied by an integral from minus infinity to infinity of f of x times by e to the minus I omega x. And now we're integrating over the variable x rather than the variable omega. If we substitute in the value of f of x, we get e to the minus x squared over 2, and this can be combined with the already existing exponential. So we get c of omega is equal to 1 over 2 pi multiplied by the integral of e to the minus x squared over 2 minus I omega x. And this formula can most easily be simplified by completing the square. That involves removing a factor of minus 1 over 2, and then we're left with x plus I omega squared plus omega squared. If you can't remember how to complete the square, then you can just expand out the brackets and check that this formula is correct, remembering that I squared is equal to minus 1. From here, we can again split the exponential into e to the minus omega squared over 2 and e to the minus 1 over 2 times x plus I omega squared. And since the first exponential does not depend on x in any way, in the next step of the calculation we can simply take it outside of the integral. But we're still left with this tricky exponential involving x squared, and that can be taken care of by a substitution. So let's invent a new variable, k, and we're going to let k equal to x plus I omega divided by the square root of 2. So you can see that when we square that, we're simply going to get e to the minus k squared. And when we take the derivative of this expression to find dk, we can see that dk is equal to dx over the square root of 2. And so, substituting that into the formula is going to give us 1 over 2 pi times e to the minus omega squared over 2 multiplied by the square root of 2, coming from dx equals to root 2 dk, multiplied by the integral from minus infinity to infinity of e to the minus k squared dk. And this is a standard integral. It's an integral we know the solution to, and it's equal to the square root of pi. So that gives us square root of 2 pi e to the minus omega squared over 2, all divided by 2 pi. And so now we have an expression for c of omega, the Fourier transform of f of x. C of omega is going to be equal to 1 over the square root of 2 pi multiplied by e to the minus omega squared over 2. So let's see what we've done. We've started with the Gaussian function, f of x equals e to the minus x squared over 2. And we've taken the Fourier transform of it to find c of omega. And c of omega is equal to 1 over the square root of 2 pi times e to the minus omega squared over 2. But this is again a Gaussian function. So the Fourier transform of a Gaussian function is equal to a Gaussian function. That means that the amplitudes of the frequencies that make up a Gaussian signal are themselves distributed like a Gaussian function. Now, I like leaving my viewers with a problem, and so here's a nice problem for you. I'm going to modify f of x, the Gaussian distribution, by dividing x squared by sigma squared, and I want you to find the Fourier transform of this. In other words, how does c of omega change? Dividing x squared by omega squared changes the shape of the Gaussian distribution. A large omega makes the Gaussian distribution a lot wider, whereas a small omega makes the Gaussian distribution a lot narrower. What happens to the shape of the Fourier transform of the Gaussian function as I make it either narrower or wider?